I was sitting on my balcony on the Morosani Schweizerhof Hotel, like many of you maybe this morning, and I looked at the mountains and I thought it's very symbolic that we are here talking about these future topics in such a wonderful environment, because the mountains show us that building something needs a lot of patience. It also needs big strength, and especially when you want to climb the mountains, it often needs a team, right? Because the path is steep, it's not very comfortable, you have a big goal, and you mostly have people around you that you need to trust. There are several people in your team that you need to be reliable on, and they are experts in their thing, what they're doing. And I think that's a beautiful metaphor for the Crypto Mountain and the people that are coming here together in this room. We are not a lot, but it's not about quantity, it's about quality. And I think when I look at this room, I can see that maybe the talks that we are having here in the next couple of hours can be the base for wonderful innovations of the future. I think what's really outstanding at Crypto Mountain, and especially Crypto Mountain 2026, is that you are not looking at different topics as individual things, but as a combination. Like if we look at Bitcoin and crypto alone, it challenges the decentralization and maybe everything we know. If we look at AI alone, it challenges human tasks or what we will do in the future with it. And if we look at quantum alone, it challenges the encryption and safety in the future. But you guys are looking at all these topics together, which is really outstanding. And I look really forward to the conversations, I think, most likely in the breaks between you guys. And I really like this setup that we have here. It should be a lot of questions. We have a lot of time for Q&As, so I think the conversation that we will have here today will be very exciting for the future. And with that, having said, I want to start officially into the day. And it's not a coincidence that we start with a big quantum topic from IBM. We start with the IBM Masterclass Quantum and IBM Quantum Safe, because we all know IBM is one of the strategic leaders when it comes to the quantum space, and they have a holistic offering and a clear vision and a roadmap, which is very exciting, and I think high in value for all the upcoming conversations of this afternoon. So I would please welcome, like all of you with me together, AI architect and senior quantum ambassador of IBM, Sasha Lazarevic. I hope I said that name correctly, and I hand over the microphone to you.
Thank you, Desiree. My name is Sasha. I work at IBM. IBM in the space of quantum computing is a full stack provider. So we have hardware, software, application use cases per verticals for different industries. Research. This is quantum computing. And also we have another branch that we call Quantum Safe, with research, with consulting, and with application solutions that will help protect against quantum risks. When I say that IBM is producing computers, we have around 30 computers that are available through cloud service. Many of them, they are available according to different tiers. In these tiers, you will see also free tier. So it means that quantum computers with more than 100 qubits, they are available to everybody. You just register and you can experiment. If you would like to learn how to code on quantum computers, then you can do that. There is a limit up to 10 minutes, but it is enough actually to try small-scale problems and to learn to see how it works, your algorithms on quantum computers. Then, of course, we have the same computers, but according to different tiers for our customers or members of quantum network. There are different hardware modalities that are being used by quantum computer providers. Hardware modalities can be like photons. We use photons for quantum computations, or we can use trapped ions. We can use neutral atoms. And what we at IBM are doing, we use superconducting circuits. So these are very small electronic structures, smaller than 1 millimeter, that we put together on a chip, and that we use actually to perform the computations. So they require cooling to the temperature very close to absolute zero. So that's why they reside in cryostats. So maybe you will ask, well, okay, so it consumes huge electrical energy for that to cool. It's not very practical. I will just refer to the numbers. So current computers with more than 100 qubits, they consume 30 to 40 kilowatts of electricity. So in the future, when we build large-scale, fault-tolerant computers with much more qubits, the projected consumption of the electricity or requirement in electrical power is going to be something like 1 to 3 megawatts. So comparing to the supercomputer centers full with GPUs and these modern data centers where the electrical consumption is going beyond 1 gigawatt. So this is still small. And these computers will be able to resolve some of the problems that those gigawatt-powered GPU-based data centers will not. So we see that even though the consumption is there, the benefit for the economy is very significant of that. What can we do with these quantum computers? So we could do different things. I will just go forward to... these are different families of the problems that can be resolved with quantum computers that we believe that are very close to be usable or implementable, doable with quantum computers. Hamiltonian simulations, so this is for material science, drug discovery, optimization of all kinds, optimizing financial portfolios, optimizing the energy use, optimizing manufacturing, supply chain, all kinds of optimization problems that cannot be done on classical computers, even using the heuristics, will be able to be solved and evaluated with quantum computers. Machine learning is also where we are looking into how quantum computers can accelerate certain routines within modern machine learning pipelines. And differential equations. So this is maybe the biggest advantage, where when you have complex differential equations, usually you cannot really solve them analytically. You have to use Monte Carlo simulations. Well, this is where quantum computers can shine and can provide alternative and better way how to solve these differential equations numerically. So this here translates into different industries and different particular problems. And here is a set of use cases that we have already explored. So it is important to know that current computers that we built, I mentioned more than 100 qubits, they cannot keep the coherence for a very long time. So the maximum size of the quantum circuit or quantum algorithm that we can run is limited to something like 5,000 operations. So we are using different probabilistic techniques to reduce the noise, but they have limits. Still, even nowadays, we were able to prove that quantum computers has its utility. It means that practical problems can be resolved with that. In the future, with a quantum error correction, it's going to be completely different. We will have redundancy that will provide additional layer of protection against the errors, so we'll be able to run millions and billions of operations on our qubits. We call these qubits error-corrected qubits or logical qubits. We have on our roadmap already when this is going to be done. We have started already the experiments and proven that this can be done. So it's the matter of engineering efforts, testing, scaling, and implementing that on a real quantum computer. So now this period before we develop fault-tolerant large-scale quantum computers, we call quantum utility. So this is the era where some of the practical problems can be resolved, but not all, and not with quantum advantage. It means not better than the best possible classical computers. Two use cases here, they attracted a lot of attention last year. HSBC, they were able to prove 34% improvement over their classical trading performance in their trading process. And at the same time, there was this Vanguard use case was published. It is very interesting. We worked together with them. And what they have done on a 109 qubit machine, they have simulated the optimization of portfolios based on conditional value at risk. So they have used 109 qubits to represent 109 different bonds. And based on this representation, they developed a sample of around 8,000 different portfolios. So in each portfolio, you can include one bond or exclude one bond, and then in total you have potentially 2 to the power of 109 different portfolios. So they have created a sample of 8,000 portfolios. They extracted this, then they calculated value at risk. They cut off 10% based on these 10% worst portfolios. They've calculated the average, so this is the conditional value at risk. And then, for that, they use it as a cost function on a classical optimizer. So this classical optimizer optimized the parameters to say, again, to the quantum computer, those 8,000 portfolios that you generated, they're not good. Now you need to do better. So quantum computer generated 8,000 new portfolios, this time better. They extracted and they have run all these iterations 1,000 times. At the end, they got 8,000 portfolios with a superior performance to what they could do classically. So this is a very interesting experiment because it proves that instead of Monte Carlo simulations, they could use quantum circuit to optimize their portfolio based on conditional value at risk formulas. And this is opening the path to new experiments because then risk managers, they can take into account macroeconomic parameters, which they often want to do, but that they are not able to do because a Monte Carlo simulation explodes inside. So now they can do different loops, internal loop with macroeconomic parameters, and they can achieve much better performance, even now with noisy computers in the era of quantum utility. So this is one of the really great examples of how currently quantum computers could be used to help in financial services industry to optimize portfolios or to perform different simulations. All that, let me come back to the question of the quantum computers. So here we have hardware, software. In terms of the hardware, so you can see this is very shiny. We use designers to do this. And this is a difference from what is currently what we are using and in the future in order to implement this quantum error correction. You see, it's much more complicated. Here we have more connectivity between them, and this allows actually to, out of these physical qubits, to just extract one pure, high-quality, fault-tolerant qubit that we want to use for long-term computation. So this is in terms of the software. Qiskit is open source. It's preferred platform for developing quantum algorithms. And this is actually the roadmap. So you can focus on 2025, 2026. I mentioned here this 5,000 operations. So, and here you will see a big jump from 2028 to 2029. So this is from Nighthawk 15K to 100 million gates, 100 million operations on 200 qubits. So 200 logical, high-quality, fault-tolerant qubits. And we will continue further, combining these computers into larger systems. The idea is actually to, when we have one module of 200 qubits, we would like to interconnect these modules further, so that the qubits in one module, they can entangle with the qubits from the previous module, so they can act as one system. So this is actually the way how we anticipate to scale out further. So this here is These are the intermediary steps that we have achieved and we forecast. 2023, quantum utility, this is actually what I said already. Things like HSBC, Vanguard, and maybe 100 other similar cases with different companies and different research institutes. This year, we're going to demonstrate quantum utility, quantum advantage, so it means with error correction. Well, this is demonstration. It doesn't mean that actually the system are going to be available large scale to all end users. But 2029 is the plan is to deliver this, the first large scale fault tolerant quantum computer, as you have seen, with 200 logical qubits and 100 million gates. So what does it mean for the safety, for the security? So RSA and ECDSA protocols, they rely on public and private key encryption. So you have a private key, based on that you develop a public key. Public key is very often is left visible. And the idea is, if you want to deduct the private key from the public key, this is computationally prohibitive nowadays. It takes many millions of years on supercomputers nowadays to do it. So it is, theoretically it is feasible, but is computationally very costly and not practically doable. Quantum computers using Shor's algorithm, it has been proven that they can do it in a matter of minutes, seconds, hours. Now, performance, exact performance, how long time it takes is have not yet been mathematically proven, but it goes around minutes. We're talking about minutes. So the risk is actually for many industries, financial industry, defense industry, health industry, etc., is that hackers can harvest the data together with the public keys and then wait until there is available quantum computer in order to decrypt it and then compromise the usage of the data. So that is why many companies, they are starting to act already nowadays. There are different jurisdictions, they have issued the recommendations or directives to do it as soon as possible to move towards the quantum resilient security protocols. These are new mathematical formulas that cannot be broken by quantum computers. They have been already adopted last year by American NIST company and other standardization organizations. They are available. It takes several years actually to implement them. You need to identify where exactly, what you are going to do, what is computational cost of that, and do the rollout. You need to involve also the suppliers. Your suppliers need to be also using quantum resilient protocols. So it takes time. European Union has issued a recommendation. There is a roadmap. It is issued last year, but it is not mandatory. Switzerland has not acted yet, but many companies, they feel this is very critical for their business. So they are starting, learning, and developing their roadmaps, and already doing the discovery, and some of them, they are very advanced in their roadmaps. What does this mean for blockchain? So in terms of Bitcoin, some of the public keys in a Bitcoin blockchain, they are exposed. It means they are sitting there. Public keys are visible. So they are at risk. We can easily, with quantum computer, in the future, we can create a private key and compromise these wallets. Most of them, newer ones, they are not so exposed. They are hashed. So it means that when you hash something, it cannot be broken by a quantum computer. So they are protected while they are hashed. But let's say that, for example, you have one hashed wallet and you have 10 Bitcoins. So you want in the future, let's say that nothing happens and Bitcoin blockchain is like it is nowadays, and there is potentially a quantum computer sitting somewhere. So you want to send one Bitcoin to another wallet. The moment you generate the transaction, in the transaction, there is a public key. The public key of this transaction. This message is being broadcasted to all nodes. And during this time, from 10 minutes to 60 minutes, this public key is exposed. The miners on this network will take this, and then they will mine the new block where they are going to store the new transaction. So the new transaction, when it is executed, even if they can access the public key, the fund has been transferred. So you cannot do anything out of that. Your remaining 9 Bitcoins, they are stored with different public keys and again hashed. So 9 coins, they are going to be 9 Bitcoins, they are going to be safe. But during this period of 10 minutes, 60 minutes, I don't know how long, the public key of this transaction, it is exposed. And if any of those nodes has a quantum computer, using Shor's algorithm, will be able to deduct the private key and compromise the transactions. So this is the first risk. It means that many wallets, public keys, they're already exposed there, they're already written, including the originator, Satoshi Nakamoto, his Bitcoins, they are exposed. So the Bitcoin will have to move to new protocols. Another risk here is that proof of work is affected by another algorithm. This algorithm is not of substantial threat because it offers quadratic improvement. But adding larger, more bits to this encryption schema of the miners for the proof of work will help. Then even the quantum computers won't be able to break this encryption. There are also internet communications, they are vulnerable. Based on RSA, RSA is also vulnerable because it is based on public and private key encryption. It is important to say that RSA, for its encryption protocols, it uses 2048 bits. For that, we need 5,000 logical qubits to decrypt. ECDSA uses 256. For that, we need less qubits. So Bitcoin and Ethereum, other layer 1 chains that are using ECDSA, they are more exposed than RSA. For ECDSA 256, we would need 2,500, mostly logical qubits, in order to break. There is also the question of other networks, like Ethereum with layer 1, layer 2, Tron, Solana. All of them, they are using ECDSA. On many places, not only for the protection of the user names, user accounts, but on many places, several places. This has been identified by Vitalik Buterin, who announced already beginning of this year the creation of a quantum team. So they will tackle this through a series of projects, and they are already solutions that can be used to protect against quantum computers. But things need to be done. Bitcoin, blockchain as well. So this is one of the ideas of how this could be solved. Another touch point between quantum computing and blockchain, especially proof of work types of blockchain, is the use of quantum computers for mining. So you know that proof of work requires a lot of computational power and it consumes a lot of electricity. So there is some ongoing research on how quantum computers could be used to save costs there, to mine better. This is an interesting area. It's still not conclusive. There are different companies demonstrating the advantage, the benefit of that. Then it's going to be maybe very interesting to follow who will produce such mining devices. IBM, I don't think so. We are really working on handling important world problems, not really developing ASIC-type computers that some miners will keep somewhere in, I don't know, in cold environment and run them. So, but probably we will see some providers developing this kind of specialized equipment. Maybe it will come a bit later, so it's not really... the development of quantum computer is not so even. So we are very close to quantum advantage. Some of the other companies, they claim also, but there are still quite a lot of engineering problems. So until we come to the stage where quantum computers can be used for mining, and they are commercially viable, because they also need to be cheaper than ASIC computers, it will take some time. But this is a promising domain of looking into how to use this computational power to do also this kind of work. I skipped this slide, which shows actually what are the fundamental differences between classical computation and quantum computation. Quantum computing is fundamentally different. It doesn't rely on using data, like machine learning, like deep learning, or generative AI. It tries to exploit the natural phenomena like that happens in quantum physics, like superposition, where one quantum system can be simultaneously in two states, quantum states at the same time, which we can use to encode exponentially more information theoretically in one quantum system. And exploits also entanglement between two quantum systems where we can parallelize the operations over all these quantum states. And then we evolve these quantum states and we observe that there is interference pattern which naturally emerges through our algorithm and provides the means to extract the solution to our problem. So you see that everything happens on this level, fundamental level. It doesn't come from determining the pattern of the data. It comes from exploring the solution space. So that's why this is very practical for optimization problems, for differential equations, for simulating natural processes, simulating how atoms interact with each other, and similar things. And here you see that we don't think that quantum computers are kind of gods that can resolve everything. There is one subset of hard problems that can be resolved. So, and these are problems actually that I talked about. I will stop here. We have a couple of minutes for questions.
Also, I have a question with regard to the 6 points. Maybe you can do the slide again. These 6 activities you have to, in order to be quantum safe in the blockchain space. Does it mean that you have to fulfill all these 6, then you can say you're quantum safe?
This is the way to do.
Okay, so then you say, okay, 1 and 2 is fulfilled, but if the rest is not fulfilled, then it's not quantum safe.
Some of them, they're interdependent.
No.
Some of them, they are still important for being really quantum resilient. So I don't think we have time now to get deeper into this, but if you follow this, you will see that this is a full scale, full spectrum recommendation of how to cover for the vulnerabilities.
Okay.
And this, I think, would apply generally also for other proof of stake. This is a bit Bitcoin-centric, but the general vulnerabilities are really the same.
Okay.
Thanks a lot again for the wonderful presentation. The quantum risk, just coming to the 10 minutes which you mentioned during like the 10 minutes period where Bitcoin funds are being exposed, just to understand that again. All the funds, let's assume I have 10 Bitcoins and I want to transfer it to another wallet. Like I pay 1, so that means 9 come back to me and 1 goes to another fund. Are all the 10 exposed or like just the 1?
Just 1.
Why is that? Because I would assume during this 10 minutes period, pretty much the public key is like exposed to the world. And
because your wallet is going to create another set of private and public keys and is going to transfer 9 bitcoins to this set. So it is not going out. It's happening within your wallet and is being registered there. So 9 bitcoins are safe, but 1 bitcoin to which you engaged this transaction, it is exposed during this period while the network is spreading the information and this.
But just a follow-up question on that one, because my understanding is well that the banks, they use now the 2048 bits regarding the RSA algorithm. And you said that, of course, is currently, because just it's a bigger data set, is safer than the elliptic curves algorithm. But having said that, don't you have the issue with a public key in the RSA algorithm, which is just out there? Or do they have as well the hash function? I'm not really that familiar with the...
I'm sorry, are you talking about Bitcoin or Ethereum?
About RSA, about the RSA algorithm.
RSA, about RSA algorithm. RSA is used for encrypting the access to your email or accessing information through internet. So RSA, I don't know exactly where the public keys, if they have been broadcasted, they are not being changed. So you're still using your private key yourself. If somebody captured your private key, your public key, sorry, so they will be able to deduct.
To follow up on that question, if you're using HD wallets, which most people do to generate the next sequence of private public keys, if you're using the HD algorithm, is there quantum compromise there as well?
I'm sorry, which algorithm?
HD wallets?
HD wallet.
Heuristic wallets. So most custodians will you create a seed. From that, you will have a derivation path, and therefore the next private public key pair that you send the change to is going to be a private public key derived from the seed plus the index path. I assume there's going to be a vulnerability there that quantum will be able to kind of exploit, and at that point, all of yours are going to be at risk.
I don't know.
Okay.
I don't know. HD, I'll have to look into. But generally how it works, basically, if the public key is hashed, it's protected. So you don't need to worry about it. But
read up on HD wallets.
Yep.
Have a look.
One more question. Thank you. It was an extremely insightful presentation on the solutions. How practical and expensive are these 6 solutions, and what could happen in the transition phase?
Yeah, thank you very much. So there is a computational cost of that. And that is where the chains, they will have to experiment to see how to handle it. It can go 50 times more expensive in different layer 1 networks than currently. So we're talking about gas, and it costs. So this is why it is not straightforward. So Ethereum, Solana, other chains, and layer 2 chains also. Layer 2 chains are increasingly relying on their own cryptography. If they're using elliptic curve public keys, which most of them do, so they will have to figure out how to migrate to new resilient keys. Behind of that, there is a cost. So I think that there are some ideas as well how to bundle this, so to save on the cost, how to compress, but that's active area of research, so I don't think that they have now already a clear solution how this should look like. But that's very important, because otherwise the costs are just going to increase and it's not going to be really profitable to run smart contracts on that. So the idea is now they are looking into how you can still use the same algorithms, but in a computationally less expensive way, or how you can find the right combination. Like, for example, you have 1,000 users, million users, so probably you will be able to bundle all of them, and then instead of 1,000 times, 50 times larger cost, you have cost which is 50 times larger, but for less number of users. So there are different ideas there, so I don't know, I mean, in the end, what they are going to do, But I think in the next 1, 2, 3 years, because you have seen the roadmap. So this is, we are the leaders. Superconducting computers are the most stable and the most scalable. So I think that we will be maybe the first or among the first to reach this quantum advantage. But there are the others. So we don't know who will be the next, when this will happen, maybe 2030, 2031. But in several years, there will be the others who will probably reach the same level of scaling with a fault-tolerant quantum computation. Then that is, it comes to, it brings the blockchain in the risk. Hey!